So today I'm going to be talking about Lab 1, which is our constant velocity lab. My name is Noor Yusuf, and I'm going to be starting off with an introduction, talking about the purpose of the lab, the fundamental physics principles, and just discussing the system and surroundings and the initial conditions. And then I'm going to be moving on to the tracker analysis, where I review the tracker software that we use to observe our data. And then I'm going to be discussing the computational model, which is code that we use to give us predicted data. I'll then be talking about the results, which will compare the two data from the two graphs, and just discuss the implications of this lab. So the purpose of this lab was to observe the motion of a moving object, which in this case was an expo marker cap at constant velocity. We used a tracker software to analyze the object's position versus time from a video that we uploaded. We then constructed a computational model using code based on Newton's first law, and then we compared observed data with the predicted model on the same graph. The fundamental physical principles we used were Newton's first law, which states that an object in motion will stay in motion unless net forces act on the object. We also had to consider that the object was at constant velocity. We used two formulas. The first was the velocity update formula, which is the final velocity is going to be equal to the initial velocity plus the acceleration, which is the net force over the mass times delta t, which is the time. And we used the position update formula, which is the final position is equal to the initial position plus the average velocity plus time. Our system was the marker cap, and the surroundings was anything outside the object that might affect its motion or interact with it. For example, friction from the table, air resistance, or the initial push from the hand that pushed the marker, or even the force of gravity from Earth. Our initial conditions was that the object was accelerating due to the net force, which is the initial push from my hand acting on the object. So here's the video of the tracker software that we use to help us graph our data. As you can see, that ignoring this first part, which is just when the object is at the beginning before it starts moving, you can see that the object is moving constantly, the position's moving in a constantly upward direction, which is pretty consistent with our predictions, which we're going to see in just a few moments, and because the object is moving constantly, the position of the object is moving constantly upwards, that means the slope's constant, which tells us that the velocity is also constant. Looking at our computational analysis, the initial conditions we decided to take into account with our coding was that the initial position of the ball was 0 because it started off at the origin, which is 0 on the meter stick. Also, the velocity of the ball we started off with was 0.486, and that's just going to be the constant velocity we use for our prediction. We also ended up putting in a net force of 0 because, according to Newton's first law, we said that the net force of the object was going to be 0 because the object we wanted to see if we wanted to observe the object at constant velocity. Also, using the two formulas discussed earlier, we have our velocity update formula and our position update formula, which the code then updated with numbers to give us our two graphs. These are the two graphs we ended up obtaining from our code. We can see that, similar to the tracker software, that the position versus time graph is a constant upward line, and also our velocity is a constant line, which is consistent with our prediction, which is consistent with our observed data. Comparing the two graphs, we can see that they both have the same general trend. We can see that the x position predicted using the computational model is a little bit higher, but this is because the computational model takes into account all the resistive forces that act against the object, such as friction, air resistance, and gravity. When it omits those, when in reality, these forces are acting on the marker. For our data predictions versus our model predictions, we can see that the model prediction matches the data observed from the experiment, and that the similar initial velocities between the predicted model and the observed data. We also see that the model predicted constant velocity motion, and that the data shows that the forces do stabilize and the car ends up moving with constant velocity for the rest of the motion. Towards the end of the time duration, the position values begin to diverge from each other, and the observed velocity begins to decrease, which indicates that the surroundings are exerting a force on the cap. Because the net forces acting against it end up leading in deceleration. Possible sources of error include that the angle of our video was not perfectly in line with the ruler and the cap, which could have affected our data in our tracker. We also could have not had a small enough delta t, which could have led to not enough points in the tracker to analyze, and the differences in placements of the marker in the tracker. If our axes, we need to consider what would have happened if our axes were flipped. Only the x-axis would have been affected, and we would treat the left as if it was positive instead of the right. The direction of the position and the velocity would be opposite to what they were initially, and the magnitude of the position and velocity would remain unchanged. So what does this mean? It's not really possible to count exactly how many forces are acting on the object. In reality, the net force isn't perfectly zero because of the balance of forces acting on the object. The gravity and the normal force would cancel each other out. The friction and air resistance act against the object's motion. Other effects like surface tension or similar small forces may also play a role, so we can't know the exact number of forces contributing to the net zero situation. And that's it.